This is Honors Algebra 2 Pre-Calculus. We're doing homework review, section 9.4 in Pre-Calc, number 81, page 687. So in this particular problem, we're asked to prove the nth sum of a geometric series, okay, or of a geometry sequence. So we're asked to prove the nth sum. So notice that there's a couple little things to just take into account here. The first thing is that you're actually not starting at I as 1, you're starting at I as 0, right? And that whatever this top bound is, it's n minus 1, and on this side there's an n. So like if the top bound were a 2, this power would be a 3. If the top bound were a 7, this power would be an 8. If the top bound were a 1, this power would be a 2, right? Because n is 1 more than n minus 1. So let's walk through our proof by induction, okay? And I'm going to inch this over a little bit because this is going to take pretty much our full board to do. Okay, so the first step in a proof by induction is to prove the very first case. Now in this situation, the very first case isn't actually 1, it's when I is 0. So we're going to prove, you don't even have to prove, we're just gonna, I should use the word show, right? So we're going to show that P sub 0 works, right? That this statement works for 0. So if I were starting at 0 and ending at 0, right? Like if I'm starting and ending at 0, because that's the idea, then I'd have A times r to the 0 on this side. And on the other side, I'm going to have an a times a 1 minus r to the first, right? Because again, if I'm starting and ending at 0, then n must be 1, right? Because that's how I'd have a 0 at the top if n is 1 over 1 minus r. Well, this is an a times a 1, and that's equal to an a times 1 minus r over 1 minus r is also a 1, so I get a equals a. So, sorry, that a kind of looked like a d, but you get the idea. Okay, so that's true. So I've shown that for the very first case, which in this case is P sub 0, this statement works. The second thing I have to do, right, is I have to assume, right, I have to assume that P sub k is true, right? So I'm going to assume that P sub k is true. Now, these are much easier so we're going to assume that P sub k is true. These are much easier if I write out the first couple terms. So what P sub k would look like is a times r to the 0 plus a times r to the first plus all the way up to a times r to the k minus 1, right? Because if I'm using n as k, right, P sub k means n is k, then what that implies is actually, well, I mean, we could argue that this actually was P sub 1, right, because this is P sub 1, I shouldn't have called it P sub 0, because that would be n is 1, right, so P sub 1 means n is 1, sorry, that was a silly brain fart that I called it P sub 0. So, anyway, we're saying that this whole thing, if I plug in k for n, meaning I go up until the k minus 1 up here, right, that's going to equal a times 1 minus r to the k over 1 minus r. Okay, so this is a fact, and I'm going to need to use this fact to the hardest part of this proof, which is to show that the P sub k plus 1th case also works, right? So again, when we talk about P sub 1, what we're saying is n is 1, right? Again, that was a brain fart where I said 0. When we talk about P sub k, we're talking about n being the letter k, okay? So I have to assume that that's a fact, and I'm going to use that in a second when I do my proof. So the third thing I do, and I'm going to inch this over in a sec, is I now need to prove that P sub k plus 1 works as long as I can use this assumption, right? That's the idea, that with my induction, you're showing that the k plus 1th term works as long as the kth term works. So if I'm trying to prove P sub k plus 1, that's going to be a times r to the 0 plus a times r to the 1 plus up to the a times r to the k minus 1, which was what we had in the last expression, right? Plus the last term that would be the difference, which is the k plus 1th term. So a r to the k plus 1 minus 1, which we'll deal with in a sec, okay? And I'm trying to show that that is equal to what happens if I plug a k plus 1 in for n. So a times 1 minus r to the k plus 1 all over a 1 minus r, right? And that's a question mark for right now because I don't know that they're equal, right? So that's what I'm trying to show. So all of proofs by induction that involve equations, like this one, are going to rely on the fact that first thing I do after I write this out is I need to replace this with the fact that I had before my P sub k. I need to replace this with an a times a 1 minus r to the k over a 1 minus r. That's what I can replace all of the first terms with, but I can't replace the last term because that was added on to the end of my fact, so that's plus a r to the k, all right? And I'm still trying to show that that equals an a times a 1 minus r to the k plus 1 over a 1 minus r. Now, so my job is going to be to take this left-hand side, right, the blue piece and the black piece, get a common denominator, and when I simplify, things should kind of go my way. So the common denominator that I need, sorry, looking for a different color of marker that's sort of buried under notebooks. Well, here we go. Sorry for the delay. All right, So what I need to do, this guy's actually secretly over 1, right? I need to get a common denominator of multiplying by 1 minus r over 1 minus r. So I'm going to buy myself a little bit of space here because it's a little hard working in just a corner of the board, right? So I'm now going to clean that up. And what it's going to look like is I have this blue piece that if I distribute the a is going to be an a minus an a r to the k, right? And I have the red piece that is, if I distribute the a r to the k, is going to be a plus a r to the k minus an a r to the k times an r, which would technically be an r to the first, okay? And all of that is on top of this 1 minus r. Now remember, my other side, right, my right-hand side that I'm trying to make this equal to has an a times a 1 minus r to the k plus 1 all over 1 minus r. So I'm already good with this 1 minus r. My job is just to simplify the top so it looks like this. Well, the negative a times r to the k and the positive a times r to the k sum to 0, right? These are going to sum to a 0, right? So what I end up with is an a, and then over here I have an a times an r to the k times an r to the first. Well, I could make that an r to the k plus 1. So I'm going to have an a minus an a times an r to the k plus 1 all over a 1 minus r. Well, if I factor out a GCF of a, I'm going to get the answer I want, which we're going to do in a sec at the top of the board, because remember, I'm only supposed to change one side at a time. I can't do things to both sides. So I'm going to just transfer this over to here. If I factor out an a from here, I'm going to get a times 1 minus r to the k plus 1 all over 1 minus r equals exactly the same thing on the other side, and that is my proof by induction, right? Q, E, D. Right, my left side equals my right side, and I am all done, right? Again, I know this is kind of a tricky problem because there's no numbers, and that's a little bit off-putting, but that's the gist of how we do this problem.